Thanks, Justin Sinclair. We're going to start right on time. I am your MC, person taking speaker, and timekeeper. So we're going to try and keep this as close to time as possible. So today I'm giving two talks. The first half hour is going to be an introduction to the endocannabinoid system. And for any of you that know anything about the endocannabinoid system, half an hour is certainly enough time to get through it. But we'll get started. For any of you that do not want to know, please just send an email. That will be at the end of my slides. Just take a picture of that, send me an email, say that you like it. I'm very happy to share everything. All of the material that I'm producing and providing to you guys today is for your reference. And yes, I'm very happy to share that with you. So, good afternoon, ladies and gentlemen. Ladies and sisters, great to see you today. What I'm going to do before we jump down that rabbit hole of the endocannabinoid system is just go through, as usual, the disclaimers and things like that. So here we go. There's my disclosure. And for those of you that don't know what our pharmacologists do, I promise you it is real work. We study drugs that come from plants, other substances of natural origin, fungi, those types of things. So it's kind of like the longest cousin of pharmacists. So I've been doing this for just over 20 years. And as you can see there, there's a list of my disclosures to do quite a bit of programs like in the medicinal space. I'm currently employed as an CSO for UIC. And doing my PhD on the side. Just to show that there's a WSU, I'm a postgraduate research solution. Now, before we get going, I'd like to start with a quote from Aristotle, who basically said, if you wish to understand anything, look at its beginning and its evolution over time. So this is what we're going to do. We're going to start with a little bit of history of the endocannabinoid system, and then I'm going to immerse you into its anatomy, and then we're going to go through and look at its physiology and examples of dysfunction. So if you have any questions as you go, I'll hopefully have some time at the end, and I'll take this for you. Okay, so the endocannabinoid system, you've all heard, Lucy has said, how many of you have started today with that talk? Show of hands, how many of you have got cannabinoids in your system, and of course your hands should all be up. The question that I wish to ask you is actually a little bit easier. Is how many of you have studied the endocannabinoid system in any of your undergraduate training? Show of hands. Not one. Okay, I'm glad you're all here. Okay. So the interesting thing about that is that's the same number that we're seeing from all other healthcare professionals. So it's really important when you can, particularly for those of you that have any influence in undergraduate curriculum design, that this is starting to be introduced. It's not that new anymore. Okay, this is like 25 to 30 years old. I know that people sit there and say, oh, that's right, that's new science. We've got to move quicker. This is the information age. So any of you that have that panel would be great. So we'll start with the distribution and history. So the evolutionary development of the endocannabinoid system has taken place over millions of years, as you can see, and across diverse biological organisms. So it's not just us. The evidence of cannabinoid receptor genes have actually been found in the Deuterostomian invertebrates, the intestinalis, which is the humble sea squirt. And if you go back and look at those genes, that's 500 million years ago. So this is something that is seen across all sorts of different animals, the monkeys, vertebrates, mammals, the fish, amphibians, sea urchins, leeches, and mollusks as well. And as you can see, at 0.4 down the line is incredibly important. It's still something that we're not seeing sort of across many healthcare professions in their undergraduate curriculums. So again, it's still on their history. In the research into how phytochemicals were actually extracted and found and categorized when it comes to cannabis was actually quite slow as well, and how these phytochemicals from cannabis interacted with our own endocannabinoid system. So this was largely impeded, of course, because of inconsistent cannabis plant samples, prohibited laws over the last 80 years that stopped its availability in research, and then a poor understanding of the actual chemical structures of the phytocannabinoids, which I'll go into in the second talk today. So with advances that happened in analytical separation techniques back in the 60s, this was largely fueled by many of you who know Gayoni and Bushuman. They elucidated delta-9 tetrahydrocannabinol, or THC, in 1964. And then 3 years later, as you can see on the slide, they chemically synthesized THC, which made it easier and more available for researchers. In 1988, I believe, I was in 8th grade at that point, Rashul and colleagues demonstrated that THC was stereospecific. So it needs a specific cycle. And then from there, later that same year, the first cannabinoid receptor was actually identified for the brain, and 2 years later, its structural expression was characterized by that. So by this time, that late 80s, early 90s, the research interest really started to pick up. In 1992, the next bit of the puzzle of the endocannabinoid system, that is, what endogenous ligands we manufacture in our organism that then interact and bind with those receptors is discovered. So based on what researchers already knew about the phytocannabinoids, that they were highly prolific of fat level in their structure, it was hypothesized that the endogenous ligands, the endocannabinoids that we produce, would also be mineral-derived. And not surprisingly, this was proven correct by Devane colleagues who identified methanide, or more chemically correct, known as N-rapidinol ethylamate. I'll touch on that later. So, from there, a year later in 93, the second cannabinoid receptor was isolated, and then in 95, one of the main endocannabinoids, which is 2-rapidinol glycerol, or 2-AG, was discovered again by Rashul and Symposium. So the thing that's really interesting is on this slide, what I don't discuss is that the enzymes that are involved in both the degradation or the synthesis of our endocannabinoids. This is something that's become a really big target of pharmaceutical interest since the late 90s. All right, everything's popped up. So as such, what I want you to take home from this is that the endocannabinoid represents a very wide-ranging neuromodulatory system that's involved in the regulation of many facets of homeostasis, with cannabinoid receptors being widely distributed in many cells and tissues throughout the body. And I will show those as this talk goes. So essentially the ECS, as I will talk to, is made up of 3 major components. These components, number 1, are the cannabinoid receptors, the CB1 and the CB2 receptors, which are distributed extensively throughout the various organs and tissues of the body. Secondly, are the endogenous ligands, the endocannabinoids, that interact with these aforementioned receptors. And then lastly, the enzymes that are involved in the synthesis and degradation of those ligands. So the thing that's really important to you as clinicians is that any individual variability or genetic polymorphic modifications to someone, and any of these components that we see of those 3, can actually potentially modify the normal functioning of the entire endocannabinoid system, and then the body systems that it regulates. So this is really important because I think it invariably highlights the importance of taking a patient-centered, patient-centric approach to the use of cannabis and other cannabinoid medications in patient care. One thing you'll never see me talk about is that cannabis is for everyone. It certainly is. But for the people that it works with and the people that it helps, it really can be life-changing. Okay, so here comes the science. This is going to bring back the biological trauma from your undergrad studies, I'm sure. So these cannabinoid receptors, I'm going to talk about them generally first, and then we'll look at them specifically. So they are belonging to the family of GIO protein receptors, or the GPCRs, and are actually expressed in abundance right throughout the central nervous system. And listen to this, where they far exceed those present the neurotransmitters that they're watching. That's getting from it's enmeshed, it's everywhere. So it's not all about the cannabinoid receptors, though, as you can see on this slide, with many different receptor types expressing endocannabinoid binding, with examples being the GPR55, the GPR119, the transient receptor potential amyloid 1, and the TRPV1 receptor, which is very important around inflammation, and the peroxidome proliferator,
or the PPARs, the alpha and gamma subtypes. And you'll remember that these are actually nuclear receptors, I'm sure, from your biology. And these nuclear receptors are very important for things like gene expression, cellular differentiation, apoptosis, and cellular metabolism. Okay, they're just a couple of examples alongside with things like expression of genes. So the more that we're learning about the endocannabinoid system, the more we're actually finding out that this ECS is a web through which pretty much most of our physiological processes are firmly enmeshed within. All right, so The CB1 and the CB2 receptors, coupled to those G proteins that are within the cell, or just on the outside of it, demonstrate their physiological effects by one of three ways. So the first effect, inhibiting adenylate cyclase, that is, inhibiting the conversion of ATP to cyclic AMP, and hence also to cyclic AMP-dependent protein kinases. Justin, that's all Greek, okay? It will come, promise, I will make that make sense. Stimulating the mitogen-activated protein kinase, which are involved in various cellular responses. So looking at things here like stimuli, such as mitogens, osmotic stress, pro-inflammatory cytokines, inflammation, and therefore assist in regulating all these different cellular functions from gene expression all the way through to apoptosis, mitosis, cellular division, and cellular differentiation. So as such, the stimulation of this MAPK, as we'll call it, is a direct mechanism by which cannabinoids have been implied to impact synaptic plasticity, potentially learning, and possibly also neural regeneration and growth. Lastly, this is really interesting, the modulation of the activity of the potassium and calcium ion channels, assisting in transducing the binding of agonists. So what does this actually mean? What this does is actually looking at activating those inwardly rectifying potassium channels or inhibiting the LN and PQ voltage-gated calcium channels. And what does that do? In essence, it modulates neurotransmitter release with noradrenaline, acetylcholine, glutamate being examples. So as you can see, when we start understanding just how far this is enmeshed, particularly in the central nervous system, you can see why it's such an important neuromodulator. All right, so digging down into the weeds now. The cannabinoid 1 receptor we're going to look at. So this is the first receptor, as you'll remember, that was isolated. So these CB1 receptors are distributed extensively throughout the brain and the central nervous system. And the high CB1 levels in the sensory and motor regions are certainly consistent with the important role of the CB1 receptor in motivation and cognition. So CB1 activation, listen to this, inhibits the neurotransmitter release of GABA, glutamate, dopamine, serotonin, acetylcholine, D-aspartate, and noradrenaline of both excitatory and inhibitory synapses. So as such, what does that mean? The CB1 receptors are primarily involved in the modulation of neurotransmitter release centrally, but also have roles in causing things like coronary or cerebral dilation, neuroprotective signaling within the brain, relief of pain or nociception, and even promote neural stem cell differentiation. So those CB1 receptors are the same receptors that delta-9 THC from the cannabis binds to cause the various psychotropic and medicinal actions. So for example, here, the amygdala is responsible for emotions, fear, and anxiety. And as such, in certain patients, THC can certainly also cause this as a side effect, particularly in varieties or chemobars of cannabis that are bred to have a higher THC concentration. The cerebellum is involved with balance and motor coordination, and no surprise, THC can cause this to be impaired. The effect of THC on the hypothalamus is thought to be why it increases appetite, aka the munchies, and it may impair short-term memory due to acting on the hippocampus and alters pain sensitivity by working on the spinal cord. And the specific region in the spinal cord is actually, I believe, latest research says, the substantia gelatinosa. So of particular clinical interest then is the sparse expression of the CB1 receptor in the brainstem, specifically the cardiopulmonary centers, which explains the lack of respiratory depression with cannabis use, but which is commonly observed, obviously, in many of the medications that you would administer, such as opioids. Now, interestingly, the anti-nausea effect that you can see on this slide is actually believed to act on this particular brain structure. So the CB1 receptor is also present not just in the CNS, but also in lower concentrations in places like the peripheral neurons, non-neural regions such as the vascular endothelium, the testes, epithelial cells, the eye, and other peripheral organs. So this is quite different to the CB2 receptor. So the CB2 receptor expression is mainly in the peripheral immune cells and tissues, and is currently considered responsible for the side effects, the effects of cannabinoids having an immunomodulatory activity. So thought largely to be due to the CB2 signaling pathways playing a critical role in regulating things like microglial activities in the central nervous system. So CB2 receptors do not cause any noted intoxicating or impairing activity, but do contribute to local analgesic effects. So furthermore, the CB2 receptors demonstrate important neuroprotective and anti-inflammatory activities, with CB2 expression being enhanced by inflammation. So the receptors are expressed more when inflammation takes place, which is suggestive that this receptor subtype is involved in the endogenous response to injury. Recent evidence has also demonstrated the role of CB2 activation in analgesia in acute and neuropathic models of pain. Okay, so let's next stop on this is to the endocannabinoids. So here we've got a brief journey through these ligands, and the first one that we're going to look at here is anandamide. So anandamide is the first one that you can remember. It was named as such because of the Sanskrit word ananda, meaning supreme joy or bliss. So as you can see here, this is one of the things that's quite interesting is that with anandamide, everyone talks about it, but it's actually not the most common of the endocannabinoids, the one that's expressed the most through the central nervous system. That is far outweighed by 2-arachidonyl-glycerol, and we'll get to him in a minute. So as you can see, several other endocannabinoids or endocannabinoid-like compounds have been identified and are still undergoing research with their exact roles within the body. So here's an example of the enzymatic synthesis and degradation of anandamide. There'll be a test on this later. I'm rather severely colorblind for any of you that don't know, and my partner recently described this diagram as an affront to the Lord himself. So my apology in advance. So this catabolism or hydrolysis of anandamide is primarily mediated by the enzyme fatty acid amide hydrolase, FAAH, down the bottom there. And that degrades anandamide, as you can see, to arachidonic acid and ethanolamine. So alternatively, anandamide can be oxidized or broken down by certain cytochrome P450 enzymes, lipoxygenases, and good old cyclooxygenase 2. Now, the second endocannabinoid, 2-AG, appears to be what's called the true ligand for our cannabinoid receptors rather than anandamide. And it's actually the key in something called endocannabinoid retrograde signaling, which I'll show you in a minute, which takes place largely in the brain. So 2-AG can actually be produced in several other ways, more so than anandamide, which is actually showing us that it's more important. And current research actually suggests that 2-AG is far more abundant in the central nervous system than anandamide. So that's quite interesting. And any of you that have heard of, runner's high, and we think about opioids and all the opiates, the natural endogenous opiates that are attached to runner's high, anandamide has also been linked to that. So it's our own, runner's high, quite literally, is from these endocannabinoids. And so here, just a quick slide looking at the breakdown or the catabolism of 2-AG. So it does mimic a lot of that of anandamide. So again, same oxidative processes through cytochrome P450, the lipoxygenases, and cyclooxygenase 2. But you can see the specific enzymes are a little bit different there. And also the finishing or sequencing one there, which is monoacylglycerol lipase, so MAGL. And I think there's others such as the membrane-associated hydrolase domain 6 and 12, but that won't be in the test, okay? Now, the most important thing that I want you to look at is next. This is the thing that I think is just absolutely incredible when we start to get to learn and understand the way that this retrograde flow works. So within the nervous system, endocannabinoids are currently believed to be synthesized on demand from stimuli, such as a response to injury, ischemia, or stress. It's done in an activity-dependent manner, and according to current literature, they are not stored in vesicles like most neurotransmitters, okay? So this is achieved by the catabolism or the breakdown of phospholipid membrane components that are located in the postsynaptic neuron. So this is down the bottom here. So located within that postsynaptic neuron, once they've been manufactured, these endocannabinoids, largely 2-AG, exert their physiological effect by traveling back across the synaptic cleft and binding to cannabinoid receptors on presynaptic neurons, where they inhibit the various excitatory or inhibitory neurotransmitters. So this action is known as retrograde synaptic flow, and is actually the primary activity noted by Raphael Mechoulam of the endocannabinoids. So pretty incredible stuff. All right, so now that we've had a little bit of a look at some ECS anatomy, we're going to have a look at the physiology and the evidence gathered so far for endocannabinoid system dysfunction across some different organ systems. So with its ubiquitous distribution throughout the central and the peripheral nervous system, the ECS may play a meaningful role in various neurological pathophysiology, particularly epilepsy. So early studies have demonstrated defects within the endocannabinoid system in epilepsy patients, with one study on patients with newly diagnosed temporal lobe epilepsy exhibiting significantly lower levels of anandamide in their cerebrospinal fluid in contrast to healthy controls. So further supporting the hypothesis that the ECS may play a role in seizure inhibition in epilepsy was a study on resected tissue. So that's up on the slide here. So following surgery for epilepsy, whereby epilepsy patients demonstrated lower levels of CB1 receptor mRNA expression in the glutamatergic terminals of the dentate gyrus, in contrast to their more healthy postmortem control. So interestingly, a reduced expression of DAGL alpha was also found in epilepsy patients, which I'm sure you won't remember, or the astute amongst you might, that this was the enzyme responsible for 2AG synthesis postsynaptically. So there is growing evidence. So reduced levels of anandamide have also been found, as you can see here for, oh, sorry, wrong one, my bad. So reduced levels of anandamide have actually been identified in the CSF, or the cerebrospinal fluid, in patients with chronic migraine. So this is something that many of you may be affected by, or have patients or friends and family that are. They've actually shown some in subsequent studies that show that the gene encoding for the CB1 receptor, which is known as the CNR1 gene, being linked to a chromosomal region linked with migraine, and that variations in that CNR1 gene expression show a predisposition to higher risk of migraine development. So again, starting to see some of these deficiencies. So not surprisingly, any of you that have been in the space for some time would have heard of Ethan Russo, and he has posited a clinical endocannabinoid deficiency as being potentially critical in our pathophysiological understanding of migraine and numerous functional pain conditions, particularly things like irritable bowel syndrome and fibromyalgia. And I would hazard a guess that the more that we start researching about the endocannabinoid system, we will find that it is likely the etiology or involved in the pathogenesis of many diseases which still escape us today. I believe 45 to 50% of diseases, we still don't know the cause. So understanding more about the endocannabinoid system should bring that on. But it's not all about deficiency, okay? Excess levels of endocannabinoids have actually been noted in the literature. So point 2 here I find is of interest. As previously, this was largely, as we said, believed to be the domain of endorphins. So producing our own endocannabinoids does, during exercise and things like that, does give our new understanding for us for reward-seeking behaviors, and also gives some credence to the term runner's high. So increased levels of anandamide have been found in both the plasma and the cerebrospinal fluid of schizophrenic patients, which Jerome will be able to talk to in the third talk today, in contrast to obviously healthy controls. And furthermore, single nucleotide polymorphisms, or the SNPs, have been also described for the CNR2 gene, which, not surprisingly, it codes for the CB2 receptor. Research is therefore suggesting that susceptibility for schizophrenia may be increased by a genetically predetermined decrease in the functioning or capacity of the CB2 receptor. Timekeeper, how am I doing? Not too bad. Okay. So let's now move, that was the neurological system. Let's now have a look at the cardiovascular system. I think this is where things start to get really interesting. So what we can see here is that the ECS can certainly play an important regulatory role in the CVS physiology and the development and to progression of common CVS disorders. So studies have shown that in cases of heart failure, that endocannabinoids are produced by activated monocytes, which in turn contributes to the development of hypotension, low blood pressure, and negative inotropic activity. So reducing the force of contraction of the heart. So further research demonstrated that under pathophysiological conditions, the cardiac myocytes, the heart cells themselves, and vascular smooth muscle cells can actually generate their own endocannabinoids, which can then interact with the CB1 receptors throughout the system and can cause things like reactive oxygen species and advanced glycation end products. And what that, as they start to accumulate, that can contribute to cellular death, inflammation, and injury. Okay. So of interest here is that the upregulation of the CB1 receptor in the cardiovascular system and an increase in endocannabinoid expression was noted in the myocardium in these experimental models. So a 2012 study, I think it was by Rajesh and colleagues, suggests that the CB1 receptor promotes cardiac dysfunction, oxidative stress, inflammation, and fibrosis in things like diabetic cardiomyopathy. But here's where things get interesting, because conversely, the CB2 receptor involvement in the cardiovascular system appears to be protective. So it's kind of like a switch. CB1 is on, CB2 is off, okay? And this is protective. It activates and decreasing all of those things like the pro-inflammatory and fibrotic responses and initiating protective effects in the cardiac myocytes themselves. So the CB2 activation reduces immune cell chemotaxis. So it's reducing all those immune cells from going to the area and continuing that inflammatory cascade, inflammatory cellular adhesion, and cellular activation. So it just dampens everything down, which appears to be very protective in preclinical models of things like myocardial infarction, stroke, restenosis injury, and atherosclerosis. Now, whilst obviously a great deal more research into the influence of the endocannabinoid system over cardiovascular system dysfunction needs to take place, but it's clear that the ECS dysfunction is present, particularly when it comes to CB1 overactivity. So in various cardiovascular diseases, and that CB1 antagonists or blockers and CB2 agonists are probably of great clinical interest in pharmacotherapy for specific CVS disorders. And we know this, the pharmaceutical industry is spending a lot of time and interest in exploring these. All right, so what about the immune system? Growing research basis we can see here is starting to show that anandamide may inhibit immune function by reducing things like the production of those pro-inflammatory cytokines, whereas 2AG, acting, I guess, through the, I believe, through the 2AG receptor, not I guess, may inhibit the migratory activities of certain immune cells by modulating various pathways. So of particular interest on this slide is that studies have shown anandamide can reduce things like interleukin-6 and interleukin-8 in human monocytes, while also suppressing the release of interleukin-2, tumor necrosis factor alpha, and interferon gamma from things like activated T lymphocytes. So the latter is usually via a CB2 receptor. So this is perhaps why many autoimmune and neurodegenerative patients are utilizing cannabis and finding relief, okay? Does more research need to be done? Absolutely. But this is just the start. We're just starting to scratch the surface of how this system is interacting with our body. What about the gastrointestinal system? All of you enjoying digesting your poke bowls? Let's see what the endocannabinoid system is involved here. So most endocannabinoid activity when it comes to the GIT is mediated by the CB1 receptor under normal physiological conditions with things like your mesenteric vasodilation, acid suppression, motility stimulation, and also the secretion of gastric juices being examples. So the homeostatic mechanisms involving the GIT are listed on that slide for you, which is pretty extensive. And this is just what we currently know. So there's more coming out all the time. So with a growing research base demonstrating the connection between a balanced intestinal microbiota and normalized immune function. How many of you, show of hands, have heard that, how important the microbiota is actually starting to be shown? This is the evidence we're starting to see, okay? So expression on enterocytes, on the actual cells of the small intestine, is regulated by the enteric microbiota CB1 expression. So that CB1 expression on those enterocytes is regulated by our microbiota, with CB1 activation increasing epithelial permeability by reduced expression of the tight gap junction proteins. What does that mean? Any of that? Leaky gut syndrome, increasing inflammation, okay? So it permits that bacterial translocation and potential metabolic endotoxemia as sequelae. So blocking the CB1 expression, therefore, may help normalize intestinal barrier function, and has also been investigated for reducing obesity. Conversely, CB2 activation, just like we saw with the CVS, can exert a normalizing activity in instances of things like increased gastric motility observed in specific GIT conditions. Yeah, hopefully, have time. I've got about 2 minutes to get through 2 more slides, so almost there. So here we go, still in the GIT, the liver, as you can see here, pretty sparse population of cannabinoid receptors, but they are present. The CB1 receptor are found in hepatocytes, vascular endothelial cells, and stellate cells. And what we see here is that the CB1 activation has been associated with vasodilation, leading to things like ascites, increase in fat deposition or fatty liver disease, insulin resistance, and fibrosis, which in the liver, of course, would mean cirrhosis. Okay, so in contrast, CB2 exerts an anti-inflammatory activity, reducing that cytokine production, having the opposing effect to the CB1. So I'm starting to think, I'm hoping that you've been able to see this example of CB1 generally being the problem and CB2 being the normalizer. And in my area of research, which is the female reproductive system, so this is what my PhD is currently looking at. This is just a snapshot that research is now showing that the cannabinoid receptor distribution in the female reproductive system is quite high. So that the ECS engages in crosstalk with the hypothalamic pituitary ovarian axis. And furthermore, the ECS has been shown to influence things like uterine decidualization, follicular genesis, implantation, embryo transport, oocyte maturation, and the modulation of pain. So all of these as well, this area or region in the body has some of the highest levels of anandamide. Again, one of our numerous endogenous endocannabinoids outside of the central nervous system. So they're just 4 of the main body systems I wanted to take you through. So wrapping up this first talk, one thing I wanted to talk about was just key to understanding the endocannabinoid system is that every individual will express this with slight variability. And that's something that's really important to know. So certain individuals may express an abundance of things like the endocannabinoids, or they might have an abundance of receptors, or they may not, okay? So this is something that will change the way that cannabinoids work on individual patients. So when we start to talk about what's called the resting and functional tone, is when we start seeing those, if any changes happen to the receptor levels, if any changes happen to the endocannabinoid levels, or if any changes happen to the enzymes that synthesize or degrade those. So anything like that can change the way that this endocannabinoid system works. And obviously, because of homeostasis, the body systems that regulates, okay? So very, very important to talk about that. And we'll look at the phytocannabinoids in this next talk. So there you go. Take a picture of that if you want copies of the slides. Send me an email. Yeah, you don't have to take notes. I did say at the beginning. I hope I did. Or is it's just because I'm having an out-of-body experience talking to you guys. And there you go. There's just a couple of the references that have been used to put this together for you. So you can see it's not just all witchcraft and voodoo, okay? So quick question. Mm-hmm. An interesting question. I'll actually be able to address that a little bit in our next talk. So the reality is that cannabis obviously does have some problems and side effects with the cardiovascular system, but it's generally the components that we're looking at. THC can actually be quite problematic. CBD, on the other hand, we just need to see more research, but certainly not as much of a concern as THC. Yeah. Mm-hmm. For some systems, yes. Yeah. If there is examples of CB1 overexpression. Welcome to the world of endocannabinoid research. Yeah. It's fantastic. There's a PhD in that for you. I'm telling you right now. I got a great supervisor for you. Come talk to me after the talk. No evidence for that yet. Yeah. All right, guys. Next talk time. I hope that some of that sunk in, because this is going to be important to understand the next one. All right, let me pull up some talking notes, because this is crash course time for you. Well, if you email me, my psychic powers are a little bit waning at this time of day. That's me. Yep, you can get me there, no problem. All right, here we go. Round 2. Stop the clock, fire up a new one. Okay, guys, so it's crash course time, and I apologize in advance if this raises any grief, deeply repressed memories, or unhealed trauma from your previous chemistry undergrad studies. So if the chemical structures are simply too much to bear, please look away, I understand. But all jokes aside, I do promise I will try and make this as digestible as possible for you. So please make sure your trays are in the upright position, your luggage is stowed, and your caffeine serum levels are preferably elevated, because this is going to be pretty full on. So we'll start out with a little botany, okay, a little bit of plant science. We'll move into chemistry, and then we're going to go and finish off with a little pharmacology at the end, particularly focused on information that is clinically relevant for you. Okay, don't need to go over any of those again, because you've all seen that. So let's crack on with the star of the show. So here we've got cannabis. The Cannabaceae family is a relatively small family of flowering plants encompassing about 11 genera or genuses and approximately 170 different species. So currently, and for many years, we believe that there are largely 2 major species within cannabis, that is Cannabis sativa and Cannabis indica, but also a third that's considered, which is Cannabis ruderalis, albeit this is seen as phytochemically inferior. So more to the point, with so much interbreeding of different cannabis species and selective plant breeding programs over the years, producing hybrids or different varieties, or what we commonly refer in the industry as cultivars or chemovars of cannabis, then it's almost a moot point to actually discuss what species are being used in certain medical conditions. We need to analyze the individual phytochemistry of the plant to know what it might be useful for. Okay, so as you notice, for medicine, we typically want female unfertilized inflorescences, which is just a fancy term to explain a flower, which is made up of many smaller flowers. Okay, so here, note here that both leaves look pretty similar. Both share that classic tapered acuminate apex, the compound leaf structure, and the serrated leaf margin. But the length, width, and chemical characteristics are markedly different on these 2 cannabis plants. Whether broad or narrow-leafed species or subspecies, both share medicinal and industrial application. So here on the left, you can see a photo of the male cannabis plant. The stamens are comprised of a filament upon which the anther sits and produces the pollen. So as you can see in figure 4, the male cannabis plant produces a large amount of this pollen, and it can travel great distances on the wind. And for this reason, much like Catholic schools, is why we generally keep the males from the female plants, except for when breeding is wanting to take place. So listen to this. It's actually been noted that pollen from the Rif Mountains in Morocco have shown up on plants, on hemp plants in Ireland, some 3,000 kilometers away. So this is why many people grow in greenhouses, because we can control and stop and control the environment and stop that pollen from coming in. So if a female plant gets pollinated, why is this so important, Justin? I hear you say. It will produce a large amount of seeds, and that detracts from its ability to produce larger amounts of phytochemicals like the cannabinoids, and it can negatively impact the medicinal potency. So as such, the standard for producing medicinal chemovars of cannabis is to ensure that only unfertilized female plants, or what's known in the lingo as sensimilla, is cultivated and generally cuttings or clones are taken from these unfertilized mother plants so that they have the identical genetic makeup and assist in maintaining consistent quality of the phytochemicals. So when people sit there and say, God, how do you standardize this? That's how we standardize it, okay? So standardization of phytochemicals can be achieved. It's obviously plants and all sorts of different things can change it, but that's why. Taking these clones and making sure that they are genetically identical. So you'll notice on the right-hand side there, a hazy whitish coating on the female plant on the right. And this is not a mold or fungus, I'll have you know. This is actually another morphological structure on the cannabis plant known as trichomes, come from the Latin meaning hair. Okay, so let me just, oh, sorry, 2, 4, go back. It's having a think. And one more, come on. There we go, okay. So on this slide, what I want you to pay attention to are, these are 2 female cannabis plants. On the left, you can see the feathery looking female reproductive part, which is known as the stigma. That's where the male pollen lands on. And you can also see the glandular trichomes, which have been magnified on the right for you. And this is where the phytochemicals of medicinal interest are stored within the plant, mainly the cannabinoids and the terpenes or terpenoids. Now, hashish, you might have heard of, is a resinous extract composed of just these glandular trichomes and represents a pretty strong end product that's been used in ritual, ceremony, and medicine by humans for thousands of years. As it is essentially just purified cannabinoids and terpenes, much less is required when used as a medicine or therapeutically, although most of you would probably understand this has been used illicitly. Now that we've covered these trichomes, these are the factories of cannabinoid and terpene manufacture. It's time for the dreaded chemistry section, okay? So if you can't see up the back, I am smiling with some childish delight because this is what I love. This is my thing. And here we go. So by definition, phytochemistry is the study and analysis of the many different chemicals that exist within plants. On this amazing planet, one thing I'd love you to think about is there's approximately 250,000 species of different flowering plants. And it's estimated that we have only studied about 15,000 of these earnestly for medicinal virtue. So a pretty staggering number when you think about that. There could be some fungi lurking in Madagascar that could be used for cancer pain management. We just need to spend more money on studying our plants, and no plug from me being a pharmacognosist, but it is important. We have a cornucopia of medicines that could be waiting out there for discovery. So now that we've had a little touch on the botany and the morphology, we'll start looking at the phytochemicals. And as you can see, we'll start out with these 2, because these phytochemicals in cannabis, of course, bind with our endocannabinoid receptors, but not only cannabinoids, but other constituents that are therapeutically useful, and they will work via different mechanisms of action. So you may have all heard of, obviously, the impairing or psychoactive cannabinoid delta-9 THC, and maybe also cannabidiol or CBD, which is gaining a great deal of media attention, of course, in epilepsy, particularly the intractable types such as Lennox-Gastaut and Dravet syndrome. But there are numerous other phytochemical classes within the plant, which are, at least to me, and hopefully to you, of clinical interest. All right, so here's where I need you to be caffeinated. Let me take you through this diagram. Look at your faces. This is delightful. Now, look, I told you, I did promise you, didn't I, that this was not going to be painful. I'm going to make this as easy as possible. So we're going to move on to something that looks a little bit less like the love child of a Sydney street map and a chemistry textbook. Because, phytochemistry is fun. And this, for our purposes, will be much better. So cannabinoids, you've heard them probably being referred to as terpenophenolics, and you can see why on this slide. So right up the top there, the top right-hand corner, you can see a levotolic acid, which represents the phenolic moiety. And on the left is geranyl pyrophosphate, or GPP, which represents the terpene moiety. So these come together to form CBGA, or cannabigerolic acid, which is the precursor for all other major cannabinoid acids within the plant. It's really important to understand it's this acid form or acidic form, which is largely carboxylated, meaning that they have a carbon dioxide molecule attached that I've hopefully highlighted in blue. So if you went skipping through a cannabis plantation picking flowers and eating them, the cannabinoids exist in that acidic form, and they will not get you impaired or high because they won't bind with the correct CB1 receptor, and they will not cross the blood-brain barrier when they're in that more polar form. So far, there have been around 144 different cannabinoids that have been classified across the cannabis genus, and this is all largely dependent on the chemovar of cannabis that has been tested and grown. So all of these different cannabis plants that you'll hear, all the different types that are out there, will demonstrate their own cannabinoid or unique cannabinoid and terpene profiles, and they are all subject to environmental variables. So things like temperature change, sunlight exposure, elevation, water supply, pH can all change how those come about. So regulation and control of the environment is incredibly important for being able to achieve cannabinoid standardization. All right, so again, breaking this down so that you are absolutely clear on how this happens. In the fresh plant, okay, so again, the living plant hasn't been killed, dried, or anything yet. It's these acid forms that exist, as seen in the rectangle at the top of the slide. So not their end products, which we predominantly use as the medicine, so delta-9 THC or CBD. So once we dry and cure the plant material or expose it to heat, such as when you vaporize it in a vaporizer at higher temperature, those carboxyl groups, which I believe are highlighted there in blue, they vibrate. They start to vibrate at a really, really high frequency, and they snap off. So what that essentially does is release carbon dioxide and allows the new decarboxylated product that is formed to interact with various cannabinoid receptors and other receptor types. So when you start hearing about things like tetrahydrocannabinolic acid or cannabidiolic acid, that's the acidic form. And then decarboxylation needs to take place for it to turn into its neutral. That's the fancy term that we'd call it. So down the bottom, you can see this process of decarboxylation has been outlined for you. So changing the non-psychoactive tetrahydrocannabinolic acid, or the non-impairing THCA, into the impairing or psychoactive delta-9 THC. But the same mechanism exists for all of the major other acid forms in the plant, like cannabidiolic acid, which is the precursor for CBD, okay? All making sense? Awesome. Fantastic. Now we'll get to learn a little bit about the specific cannabinoids, okay? So THC, you've heard of, delta-9 THC. Why is it called delta-9? You can see up there, the 9th position is the double bond in the chemical structure. Just trust me, it's there. And that's why we'll see it's different to delta-8, and it's just because of a position of a double bond. So THC binds with relatively high affinity for both the CB1 and the CB2 receptors in the central nervous system, okay? So very similar to that of our own endogenous anandamide that we made. So this constituent is associated with the feeling of impairment or psychoactivity, and if given in high isolated doses, can certainly cause dysphoria and potential paranoia and anxiety in certain individuals. So pharmacologically, THC is well described as an analgesic in the management of pain related to cancer, muscle spasm, migraine, phantom limb pain, the muscle spasticity associated with multiple sclerosis, and perhaps is best known also as an appetite promoting agent for cancer and AIDS patients, and also reducing the nausea and vomiting caused by chemotherapy. So less well known is evidence supporting its use for lowering things like intraocular pressure in the eyes, in those that are suffering from something like glaucoma. And it's also been seen to reduce symptoms in Alzheimer's disease. So CBD, on the other hand, is a non-impairing cannabinoid. Now, you'll sometimes hear people say that CBD is non-psychoactive. Have any of you heard people say that? Oh, don't worry about CBD, it's non-psychoactive. That's not true, okay? Because a psychoactive substance is anything that can change mood, cognition, and things like that. And as we can see, it's an anxiolytic, it's an antidepressant. So guess what? It is a psychoactive substance. So we prefer to say that it's non-impairing, okay? Or it's non-intoxicating. This is much more important because otherwise we're using the wrong terminology. So CBD, as we said, actually opposes in many instances the dysphoric effects of THC, which is why it's of benefit. Many clinicians, particularly doctors that are prescribing, will prescribe both THC and CBD together in varying amounts depending on the therapeutic indication that they're wanting to treat. Now, unlike THC, CBD has a very low affinity for binding to the CB1 and the CB2 receptor, but rather works via different mechanisms of action, as you can see on the next slide that I've got prepared. But this is, it exhibits serotonin binding activity. That's why it has that antidepressant and anxiolytic activity. That's through the 5-HT1A receptor. And due to CBD's antioxidant, anti-inflammatory, and neuroprotective actions, it holds great interest in treatment of seizures, epilepsy, Parkinson's disease, Huntington's disease, multiple sclerosis, and Alzheimer's disease. So as I'm sure you've noticed, or I hope you have, that some of these pharmacological actions have actually been highlighted across THC and CBD, and that they're shared across these two constituents. But the thing that I want you to remember is that in many cases, this will actually be by different mechanisms of action, okay? So what pharmacists might term a dirty drug, but this is potentially why cannabis is so effective for certain clinical indications in certain people. But this is just 2 cannabinoids, okay, out of the 144, and there's more as we count, but let's have a look at some of the others. But before we do, just adding on from the previous slide, one of the things that's important to see here, there we go, are the examples of the receptors there for THC that you can see that partial agonism with the CB1 and CB2, but looking at cannabidiol, it's an agonist of the 5-HT1A, again, the serotonin receptor, TRPV1, really important for inflammation, TRPV2, the glycine receptors, and the PPARs as well. So one phytocannabinoid binds into all these types of receptors. So this is probably why, as more research is conducted, we're going to find that CBD and the endocannabinoid system in general will start to highlight why diseases occur and maybe point to etiology. But it's not just about those 2, of course. They've had the lion's share of research, old THC and Delta-9. But as we can see here, there's others. So there's Delta-8 THC, which exhibits less impairing or intoxicating activity than Delta-9, but still exhibits many of the same useful therapeutic benefits of its stronger cousin. You've got the THCV, tetrahydrocannabivarin, exhibits anticonvulsant activity similar to CBD and cannabivarin, and is also of interest in improving things like glucose tolerance in type 2 diabetes, which of course all of you would know is still a very big problem around the world, particularly here in Australia. Cannabinol, CBN, and cannabigerol share the ability to decrease the proliferation of keratinocytes and therefore are undergoing studies when it comes to psoriasis. So whilst a large amount of these actions that you can see on that slide have only been explained or described in vitro and in vivo or animal models, it really does highlight, I think, how much more there is to this plant from a research perspective, and it's not all just about THC and CBD. Okay, so one thing I want you to remember as we start to move into the next slides is that cannabinoids, just like I mentioned at the start, are highly lipophilic, okay? They love fat, they cross the cell membrane very easy, and when inhaled, they cross the blood-brain barrier very quickly and can have a rapid onset of action. However, when they're ingested orally, they're metabolized by the liver. So THC gets metabolized into a product called 11-hydroxy-THC, which is far more therapeutically potent and also has a much longer duration of effect than in inhalation, whether that's smoking or vaporization. So here you can see how selecting the appropriate dosage form is as important in a way as selecting the right chemovar of cannabis for the individual and the clinical indication that they have. So here on this slide, just a quick one that I designed, nice and bright, which is just showing the major and some of the minor cannabinoids. So what we're going to do now is kick on and just have a look at a completely different class, again manufactured in the trichomes, and these are known as the terpenes. So as I'm sure you remember, the terpene class is also found and held within the glandular trichomes of the cannabis plant. So it's this phytochemical class that largely contributes to the unique tastes and smells associated with the different cannabis varieties. So you can think of these, if you will, as the essential oils that the cannabis plant produces, and they are not unique to the cannabis plant, but are commonly and abundantly distributed throughout many different plant families and species. So up the top there, you can see limonene, and it's responsible for the smell of many citrus species. What you might not know is that this little terpene packs quite a therapeutic punch by not only having strong anxiolytic and even antidepressant activity, but also showing evidence for use in things like gastroesophageal reflux disease. It has a moderate antibacterial activity and has also been shown to produce cell death in breast cancer cell lines. These antioxidant and anxiolytic actions that you can see highlighted in blue are also shared with CBD, but occur via a different mechanism of action. Having multiple phytochemicals within a plant that exhibit similar pharmacological activity increases the potential therapeutic activity of the medicine and is something old school herbalists would call phytochemical synergy, and it's something that researchers and medical practitioners in this space call the entourage effect. So you may have heard of that. So next one, we've got beta-myrcene. So this monoterp, so it's just got 10 carbons, exhibits the muscle relaxant, sedative, anti-inflammatory, and analgesic activity, which, as you know, are actions also shared by THC and CBD. So at concentrations at about 0.5% of beta-myrcene and higher, this is where we start to see the well-known couch lock phenomena. So it's not that specific on THC or the level of THC, but the higher the level of beta-myrcene, it can really have a relaxing effect. So these two constituents work in tandem. And do any of you, of course, love the pine smell, the smell of pine needles and things like that? And that's the last guy down there. That's alpha pinene. And this particular monoterp exhibits anti-inflammatory, bronchodilatory activities, which of course, as you can see on that slide, are also shared by THC and CBD. So here's just a little list of the terpenes that exist across the cannabinoid genus or the cannabis genus, with over 200 being currently identified in cannabis alone. So another worthy of note is the soothing and sedative qualities of linalool, which you may have heard comes from lavender. And this calming terpene is useful in anxiety and is actually found in a 1995 study to have anticonvulsant activity. So as you can see, there exists a great deal of crossover when it comes to just these two chemical compounds. And here's where things get really interesting. So cannabinoids and other pharmacological active phytochemicals, such as the terpene class within cannabis, as I've said, are highly lipophilic. So the dosage form of how the cannabis is administered is also highly clinically relevant for the individual patient and the condition that's being treated. So this may determine actually the difference between treatment failure and the amelioration of symptoms, and also other factors such as the duration of effect and potency of the medicine. So typically encountered dosage forms include things like capsules, sublingual sprays, like you might see with Sativex, edible dosage forms, infused oils, tinctures, soft extracts, concentrated extracts. Vaporizing is becoming more popular in Australia, particularly for breakthrough pain, and topical oils. All of those have been kind of characterized here. Now, each of these different dosage forms will impact the way the chemistry is absorbed. For example, orally ingested THC-rich dosage forms, like oils, will undergo biotransformation in the liver. And that will change it into a stronger form, but that will generally take anywhere between 30 to 90 minutes to take effect. However, it will have a longer duration of activity, whereas, and that's generally anywhere between 6 to 8 hours. Whereas inhaling or vaporizing cannabis will provide a much quicker onset of activity, but a shorter duration of effect. How quick? Usually 5 minutes. Maximum generally 10 to 15 minutes, okay? So for someone that's suffering breakthrough pain, that's really important. They don't want to have to wait so long, and certainly if they don't have access to intravenous. And so how long does it last? About 2 to 3 hours, okay? So what you'll find is a lot of patients will actually use oils, particularly to help them sleep and get them through pain-free throughout the night because of that longer 6 to 8 hour duration of effect. And then they'll use the oils throughout the day. And generally only if they have breakthrough pain will they actually turn to vaporizing cannabis because of that fast onset of action, and it's easier for them to dial in that titration. So all of that is important when it comes to considering these things. So generally in Australia, the things that are important to understand is that it's the oral products that are mostly prescribed, the oils, and there's some capsules and things like that. And then cannabis flower or dried flower is actually starting to grow. So this is largely, particularly seen in chronic pain. Okay, how are we doing for time? Good-o. So let's have a look at some pharmacology. So inhalation does appear to be the most common vehicle for delivery for recreational users, but also users that identify as medicinal in overseas jurisdictions, and even those that use cannabis illicitly for therapeutic purposes here in Australia. So this includes the usual things like pipes, bongs, joints, but many of you might not know is that between 30 to 50% of the cannabinoids or other active constituents may be lost during pyrolysis. So when you burn it, you're losing things. So that's why vaporization makes a lot more sense, because you're lowering that temperature and you're actually being able to yield and capture more cannabinoids and terpenes. So this being said, many patients prefer the method due to the fast onset of action, which, as I said, sets in within about 2 to 5 minutes, as it bypasses that much slower first pass hepatic metabolism for oral use. So its bioavailability is variable, but THC tends to have a bioavailability of approximately 25% through the inhaled route, and the duration of effect of smoked cannabis, as I said, typically lasts between 2 to 4 hours with a mean or median of about 3. So this does not take into account the huge variability in the THC or the CBD concentration in not only the dried cannabis flower, but also a finished medical product. So hence the importance again of standardization of medicinal cannabis products for reproducible results, because that's actually something that stopped doctors prescribing cannabis back in the 1800s, is the fact that they were getting all of that cannabis shipped over from India, and it was just of varying quality, and doctors wanted reproducible results, so cannabis started to fall out of favor. All right, so next slide here, supporting that previous assertion I made about regarding inhaling, particularly smoking being the most prevalent dosage form. This study by Professor Nick Lanzaris and the team at the Lambert Initiative and his colleagues clearly demonstrated that smoking is by far the most commonly used dosage form in people using cannabis for therapeutic purposes in Australia, but not accessing legally supplied products. So that is to say, people using products from the black market or the green market, as it's commonly called, for therapeutic purposes. But please note that inhalation via vaporization via medical prescription is on the rise, particularly for pain conditions where that fast onset of action is required. And I would certainly imagine most doctors are going to be only prescribing flower if vaporization would be using, because it's a much less harmful on the lungs because there is no pyrolysis and you're not getting any horrible end products. All right, let me just go back here. It's having a moment. No. Okay, good. So this graph you can see here shows the THC from smoked cannabis. And this is fast and steep. It's like a rocket ship. It starts to substantially decline within that first hour of administration. So just like I said, very, very fast onset. THC is metabolized, as I said, to 11-hydroxy-THC, which is the main active metabolite of THC, with some authors actually suggesting that it's either equipotent or more potent than THC. So THC carboxy is the main inactive secondary. That's the one down the bottom there on the bottom point. So this is the main inactive secondary metabolite, which is formed by the oxidation of that 11-hydroxy. So THC carboxy undergoes further conjugation with glucuronide, and that forms all sorts of other goodies, which are water soluble, so it's easier for the body to get rid of. And that's why you can have a urine test and it will pick up these metabolites. Come on. Okay, there we go. So CBD, also highly lipophilic, and this basically, for all intents and purposes, the pattern for CBD is similar to that of THC when it comes to the inhaled route, okay? So it exhibits that average systemic bioavailability of about 30 to 31%, and is not, as I've said, not actually non-psychoactive. So it has actually even shown antipsychotic activity via working on numerous receptors such as the GPR55, TRPV1, and of course the 5-HT1A, and Jerome Saris will be talking after me, particularly on the region of mental health. So moving to vaping, so vaporization, these vaping rates, as I said, are starting to grow in the medicinal cannabis users, particularly in Australia, and those of a younger age and higher education, according to a study by Cranford. So in this study, researchers found that vaping was seldom used as the sole route of cannabis administration, but was used in combination with many others, particularly oral forms. So vaporization and smoking provide comparable cannabinoid delivery, with a few differences being observed between smoking and the vaporized blood cannabinoid pharmacokinetics. However, just like smoking, different types of substances can be vaped or smoked, such as simple dried flower, all the way through to really potent oil-based concentrates that you might see in over in the United States and Canada. And they're just pure cannabinoids and not something that we see prescribed over here in Australia that much. So yeah, that's the onset of action, the duration of effect, and the bioavailability are all essentially comparable without any of the major negative effects. So in Australia, it's the oral infused oils are definitely the most commonly prescribed dosage form by far. And they have a very different pharmacokinetic profile than that of smoking. So absorption is generally considered to be intact, but has limited bioavailability due to extensive hepatic first-pass metabolism, with recent evidence suggesting eating a lipid-rich meal can actually increase, before you dose, the absorption rate. So that again, onset of action, 1 to 6 hours, but typically the average is between 1 to 2, and duration of effect, 4 to 8 hours. And here you can see again the graph that oral cannabis progresses very slowly and is actually the metabolite 11-hydroxy-THC, which is far more pharmacologically active. So tissue distribution of THC and its metabolites is currently considered to be governed only by the cannabinoid specific cannabinoid physiochemical properties with no relevant transport process or barriers impacting upon the concentration of the actives in tissues. Now, approximately 90% of THC in blood is distributed to plasma, with 10% to the red blood cells. 95 to 99% of the plasma THC is bound to plasma lipoproteins and to a lesser extent albumin. So you can see here that this again is just showing the tissue distribution, which you'll see in other panels over the weekend, is why you can use cannabis, and particularly regularly, it starts to sequester in fat because it loves that fat. And you could be non-impaired 2 days since you've used cannabis, be pulled over at a mobile drug test, swab the tongue, and you actually test positive. So this is a really big challenge for patients and for their doctors at this time. And lastly, getting close to the end here is just the cannabis metabolism. So metabolism of THC and most other cannabinoids will happen via the enzymes of the cytochrome P450. And it's worthy of note that these are demonstrable variation between mammalian species. So a lot of the studies that have actually been done, this may not extrapolate over to humans, but a lot more research is currently being done when we look at the effect of the cannabinoids on the metabolism of the cytochrome P450 because of other drugs. Elimination, you can see here, and we've already talked about that THC carboxy. So this is how it gets excreted, how it gets changed from being quite fat soluble into something that's quite water soluble, so we can get rid of it in the urine. So it can be detected because of its fat solubility on the tissue, in the blood, and also through urine. And these are the standard ways that it's tested for by police officers in mobile drug testing. And lastly, very important to bring this talk to a close. I'm just a little bit over, so I hope Jerome doesn't mind. So I need to highlight, that it's not all milk and honey when it comes to medicinal cannabis. Adverse effects, drug interactions, specific conditions such as cannabis hyperemesis syndrome are all well reported in the literature, but I would literally have to give you a talk for an hour just to cover those. But particularly things like drug interactions, I want you to be cognizant of. They do occur, they do happen, whether they're pharmacodynamic or pharmacokinetic. So currently the majority of pharmacokinetic interactions, which you can see here, which, as you know, I think they're more dangerous because they're more difficult to predict in contrast to our pharmacodynamic ones. So these are actually associated with CBD. So remember to check all the medications your patients are taking against interactions with cannabis. Adverse effects and drug interactions could really be, as I said, its own talk. But as you can see on this slide, these are just some of the currently known interactions that clinicians need to be careful of. And typically when it's around CBD, most of these observations have been in kids taking CBD for intractable epilepsy, and the doses that they're using are really high. So you're looking at, anywhere between 10 to 20 milligrams per kilo, up into the hundreds and hundreds and hundreds of milligrams of CBD, whereas that generally is not what we see with many adults that are taking it. So keep that in mind, and particularly keep it in mind when it comes to drugs of narrow therapeutic index. So things like warfarin and all those kind of goodies, cannabis can interact with them. So it's not a panacea, it's not without its dangers, but it can certainly be quite life-changing for patients that it benefits. Just finishing up, because I've got to actually hand over to, I can come and see you after. So look, guys, thanks very much for keeping me company through this basics of cannabis botany. I know it's been a little bit hectic, very unique medicine. It's fantastic to see nurses taking an interest and also leading the charge when it comes to this reintroduced medicine. I need to make that really clear. This isn't a new medicine, guys. It's been prescribed by doctors in this country, 50, 60 years ago. So it's just being reintroduced into the medical armamentarium. And thank you for being a part of this